Welcome to this explainer, everyone. Today we're embarking on a truly fascinating journey for all you FSC and DP 803 students out there. We are going to travel straight into the very center of the atom, uncovering the deep mysteries of atomic structure. We'll be moving all the way from the earliest historical discoveries right up to the mind-bending realities of modern quantum mechanics.
I want you to just stop and imagine the microscopic world for a second. I mean, we interact with solid objects every single day, right? But what exactly is happening inside an atom, that fundamental building block of literally all matter? Okay, let's dive into this and unravel the atomic puzzle piece by piece.
Here's our high-yield roadmap for today. We're going to cover 1. The fundamental particles, 2. The Rutherford and Bohr models, 3. The hydrogen spectrum, 4. X-rays and atomic number, 5. The quantum atom, and finally, 6. Electronic configuration. Don't worry, we'll cover every crucial syllabus point step by step.
All right, let's get right to it. Section 1, the fundamental particles.
So, to understand the atom, we obviously had to identify its basic building blocks first. For the longest time, scientists only knew about the negative electron and the positive proton, but the math for atomic mass just wasn't adding up. Enter James Chadwick in 1932, and this brilliantly illustrates his experiment. By directing a stream of alpha particles, these tiny positively charged packets of energy, onto a beryllium target, a highly penetrating, completely neutral radiation was produced. These were neutrons, particles with zero charge but with actual mass.
When we compare these three particles, the differences are absolutely striking. The proton and neutron both sit right around 1 atomic mass unit. They're the heavyweights. But the electron? It's astonishingly light. To put that into perspective, its mass is roughly 1,800 times less than a proton. The electron is essentially a featherweight buzzing around those heavy particles sitting packed in the nucleus.
Which brings us perfectly into Section 2, the Rutherford and Bohr models. Once we knew the particles existed, the next massive puzzle was figuring out how they actually fit together. In 1911, Lord Rutherford performed his classic gold foil experiment. Now, what's really interesting about this slide is the path of those alpha particles. The vast majority pass completely undeflected, straight through the foil. But a tiny fraction are deflected at large angles, or even bounce right back. This was a total game changer. It proved that the atom is mostly empty space, with an incredibly tiny, dense, positively charged core called the nucleus.
But, well, Rutherford's model had a fatal flaw. According to classical physics, a moving, charged electron orbiting a nucleus should continuously emit energy. If that happened, its orbit would just get smaller and smaller until it literally collapsed into the nucleus. The atom would destroy itself. To rescue the atom, Niels Bohr stepped in, using Max Planck's quantum theory. Bohr proposed that electrons don't just orbit anywhere. They exist only in permitted quantized energy levels, or stationary orbits. While hanging out in these specific orbits, they do not lose energy.
Bohr's theory was beautiful on paper, but it needed solid proof. That brings us to Section 3. The hydrogen spectrum.
When you heat hydrogen gas, it emits light, but it doesn't emit a continuous rainbow like sunlight through a prism. Instead, it emits very specific, isolated, sharp lines of light. Think of it like a staircase. When an electron absorbs energy, it jumps up to a higher, excited orbit. When it falls back down those stairs, it releases that exact, specific packet or quantum of energy as a photon. Because the orbits are quantized, the energy emitted gives us distinct spectral lines instead of a continuous blur.
Depending on which specific stair or orbit the electron falls back to, we get different spectral series. If it falls all the way down to the first orbit, we get the Lyman series, which is entirely invisible in the ultraviolet region. But here is a super important exam tip. The Balmer series, which happens when electrons fall back to the second orbit, is the only series that appears in the visible light region. The remaining series, like Passion, Bracket, and Fund, all fall into the infrared.
Moving right along, let's check out Section 4, X-rays and atomic number.
In 1913, H.G. Moseley analyzed the X-rays emitted by different elements. He discovered a mathematical relationship between the frequency of the X-rays emitted and the atomic number of the target element. So the crucial point is this. Moseley proved that the physical and chemical properties of elements depend fundamentally on their atomic number, the number of protons, and not their atomic mass, like everyone previously believed. This was huge, folks. It laid the foundation for the modern periodic table we use today. Okay, buckle up. Welcome to Section 5, the quantum atom.
This is where classical physics gets completely overturned and the universe gets a little, well, strange.
Just look at how incredibly fast our understanding evolved over just 3 decades. From Planck proposing energy comes in tiny packets in 1900 to Bohr's orbits in 1913. But then, in 1924, Louis de Broglie dropped an absolute bombshell. Matter behaves as both particles and waves. Yeah, you heard that right. And by 1927, Heisenberg introduced his uncertainty principle, cementing the mind-bending realization that the microscopic world is governed by probability, not certainty.
Let's move to and see how this builds our modern understanding. Heisenberg stated that you can never, ever know both the exact position and the momentum of an electron at the exact same time. If you measure one accurately, you completely lose the other. Therefore, Bohr's idea of a neat, fixed classical orbit had to be thrown out the window. Instead, we have the quantum orbital, a messy, three-dimensional probability cloud where an electron is simply likely to be found.
So how do we find anything in this cloud? To locate an electron within these probability clouds, we use a brilliant address system made up of 4 quantum numbers. And definitely note this down, it's essential for competitive exams. The principal number tells us the main shell size and energy. The azimuthal number dictates the shape of the subshell, whether it's S, P, D, or F. The magnetic number tells us the orbital's orientation in 3D space. Finally, the spin quantum number indicates the direction the electron is actually spinning.
We finally reached our last topic, Section 6, Electronic Configuration.
Now that we know the addresses, we're going to empower you to map out exactly where these electrons live. There are 3 golden rules, high-yield facts for your exam that dictate how we build these configurations. Step 1, the off-bow principle, tells us to always fill lower-energy subshells first. Step 2, the Pauli exclusion principle, dictates that a single orbital can hold a maximum of 2 electrons and they must have opposite spins. And Step 3, Hund's rule, says that for orbitals with the exact same energy, you've got to fill them singly with parallel spins before you start pairing them up. Kind of like people taking empty seats on a bus before choosing to sit next to a stranger.
Let's look at a quick solved example. Notice scandium, element number 21. Following the Aufbau principle, after the argon core, the 4s subshell is actually filled first with 2 electrons because it's slightly lower in energy than the 3d subshell. Only after that does the 21st electron drop into the 3d orbital. As you move down the list towards krypton, you can see Hund's rule and Pauli's principle perfectly mapping out the electron structures of all these transition metals. It really is like a giant puzzle falling perfectly into place. Wow, we've covered incredible ground today, from Dalton's solid spheres all the way to the complex, shifting probability clouds of modern quantum mechanics. I want to leave you with this final, provocative thought. If the very foundation of matter is built on uncertainty, if we can never truly know exactly where a particle is and where it is going at the exact same time, how does this quantum blur change your fundamental view of the universe we live in? Think about it. Thanks for joining this explainer, and keep exploring chemistry.